Good morning, guys, and welcome to our third day of the coronavirus-induced NTI. Um, right now, we're still looking at 2 weeks, but who knows what's going to happen. I just saw a message that the United States has shut down borders, and Canada shut down their borders, so it's getting kind of crazy. We are talking about the properties of quadratic functions in this set of notes. Before I go through this set of notes real quick, I do want to mention that I would like to get together with you guys at some point this week through a Zoom chat. That way we can get together kind of face to face virtually and talk about any questions you guys may have, address anything that's on your mind about the class, or just talk in general. But just to kind of keep a little bit of some semblance of normalcy going for us, so that we can at least get together and just talk instead of having to send messages on Remind all the time. If you don't have any questions about the class, that's fine. If you just want to get on there and just kind of hang out and listen to everybody else talk, and maybe something will jog your memory about a question you may have, we'll do that. I sent a message out yesterday. Only 2 replied, and there was not really any indication about what would be a good time today to have a Zoom classroom meeting. So I will probably defer this until tomorrow. I'm hoping you guys will watch the video today, see this message, and then get back with me and let me know what time on Thursday, March 19th, would be a good time to have a Zoom classroom meeting. I realize you guys are busy, and I don't want to. I know some of you have jobs, so I don't want to interfere with anything like that, but I do just want us to get together and keep things kind of somewhat fluid and moving in a smooth transition here as we go completely online. Properties of quadratics. Quadratics can be used to model various situations. The initial example that I show you right here, we have this number of calculators sold, represented by the variable x, is a function of the price of the calculators. So we have the number of calculators sold being x equals 21,000 minus 150p, again where p represents the price per calculator. Well, we can use that to generate a revenue function. Revenue is the number of products sold times the price. Well, the number of products sold is a function of the price. We have that expressed up here at the top above the table. So if we simply replace x with the 21,000 minus 150p, we end up generating a quadratic function that gives us a model for the revenue for this particular calculator company. One of the things we need to understand about quadratics, the parent function of every quadratic is x squared. Anything else is a transformation of x squared. And the first thing we're going to look at are compressions and stretches of the graph of x squared, and then we're going to look at reflections, and we're going to keep building onto these different transformations. So when we multiply a function by a value that is greater than 1, in this case, if we take x squared and we multiply by any number that is larger than 1, we're going to get what's called a vertical stretch. So if you think about a parabola, if this is the graph of x squared and I multiply it by a value greater than 1, it's going to pull those arms in towards one another, and it vertically stretches that graph upwards. If I multiply the same x squared function by a number between 0 and 1, then I get what's called a vertical compression, and that graph flattens out. The arms get pushed away from one another. So what you see in the middle of your screen right now is 3 graphs. The first graph that I want you to look at is this graph of x squared. That is our parent function. Everything else is a transformation of that. So the red graph represents x squared. Then we're going to look at this second graph right here in blue, which is the graph of 3 times x squared. So we've taken the graph of x squared, we have multiplied it by a number greater than 1, and you can see that the arms of this graph are closer together. This graph has been vertically stretched, and the third graph does just the opposite. Our third graph is 1/2 x squared. So now we're multiplying x squared by a value that is between 0 and 1, and we get this black graph on the screen that has the arms are spread out a little bit further than our parent function of x squared. When we look at negating all of those values, just multiplying the entire x squared function itself by a negative. These are the same three graphs that we had previously, but every one of them has been flipped over the x-axis. The way that we have accomplished that is all three of them have been multiplied by a -1. So multiplying the function by a negative flips it over the x-axis, or what we call reflection over the x-axis. And now the graph would open down. So if the coefficient on x squared is positive, the graph opens up, which means we have a minimum value, that trough at the bottom of the parabola where the vertex lies. And then when we look at multiplying that function by a -1, we get a parabola that opens down, which means we have a maximum value at the peak of the graph where the vertex lies. So let's first go into this example 1, where we're going to use a technique of completing the square, which we have talked about a little bit, and we're going to write the expression in vertex form. Vertex form, I just highlighted for you, is a times x minus h quantity squared plus k, where h and k are the vertex of the parabola. We're going to take this example 1 and we're going to rewrite it in vertex form, and then we're going to graph it. We're going to use a calculator. We're going to kind of put a bunch of different things together here. But let's first start out with simply writing the expression that we're given. And the next thing that I want to do is, it's nothing fancy. We're going to put parentheses around the quadratic and the linear terms. Function value is still the same. I've just put these parentheses around this because I'm going to do something with the parentheses that's going to make this easier to work with to write it in vertex form. So I notice that 2x squared and 8x both have a 2 in common. So I'm going to factor that coefficient, or that constant of 2, out. And now I have x squared plus 4x plus 5. Now there's a reason I didn't factor an x out as well, because I'm still trying to keep this as a quadratic. If I factor the x out, then I'm generating linear terms, and that's no bueno. We want to make sure that we're doing what we need to do to keep this a quadratic. So with this technique of completing the square, I'm going to focus on what's inside the parentheses, these parenthetical terms. I have x squared plus 4x. I'm going to take the 4, the coefficient on x, and divide it by 2. We're just cutting it in half. You're going to do this every time if you're completing the squares, cut it in half. So when I cut 4 in half, I get 2. Then I'm going to square that value, and now I have 4. So I go back to the function that we started with here, and I'm just going to rewrite it, except now I'm going to add that 4 that I just generated over here on the right in pink to the parentheses, and then I have plus 5. Now, what I have done now has completely changed the value of our given function, because we've added that 4 in there, and nothing about this function is now the same as what we started with. So what I want to focus on is, I have this 2 outside of the parentheses. If I multiply 2 by 4, I'm going to get 8. So what I want to do with that 8 now is actually subtract 8 from my constant. So I've added 8 inside the parentheses. I'm going to subtract 8 on the constant. 8 minus 8 is 0. So I've in effect added 0 to this function, which is, I won't really say it's a mathematical trick, but sometimes it does become necessary to come up with fancy ways to add 0 into a function to make things more manageable. The further along you go into math, the more practical that becomes, the more times you'll see where that is useful. But in this case, we're just adding 0. It's going to be a positive 8 and a negative 8. We just have to remember that we have this 2 times 4, which led us to the conclusion that we needed to subtract 8 from the constant. So what's nice about the technique that we're using here is my parentheses are very easy to factor. Half of my linear term is 2, so this trinomial that's inside the parentheses just factors into x plus 2 quantity squared. And then I have 5 minus 8, which simplifies to negative 3. So this is the final form That is the vertex form of the quadratic that we began with, 2x squared plus 8x plus 5. I can glean a lot of information from this, but I'm mostly interested in finding the vertex of that parabola. So the vertex can be expressed as h comma k, and a good rule of thumb, whatever your h value is, just change the sign in front of it. So we have a positive 2 here, so we're going to put it down as a negative 2. And then for your k, keep the sign that's in front of it, which is negative 3. The reason we change the sign in front of x is because of, in the vertex form, the general vertex form, it's a times x minus h quantity squared. So the only way that this could be x plus 2 is if it was x minus negative 2. So that would make our h a negative 2. Now we can plot the vertex here, which is negative 2, negative 3. And this parabola is being multiplied by 2. So that means we're going to get a vertical compression. It's not reflected. So we can kind of just get a rough sketch of this graph. It's going to kind of look like this. Maybe even closed up a little bit more, but it's just a rough sketch. We can verify this on the calculator on Desmos. Let me pull that up. Yeah, I've already graphed it once and I forgot to clear it off. So we have 2x squared plus 8x plus 5. So that's the original function that we started with. Our vertex is right here. You can actually click on it on Desmos. I know with the TI Inspires you got to do a lot of steps to get the vertex, but here on Desmos it makes it really simple. Click on it and we get negative 2, negative 3, which fortunately is exactly what we came up with when we did completing the square and we computed it algebraically. I encourage you to do both the algebra and verify it graphically, at least up until a point where you are comfortable doing it algebraically, and then at that point go ahead and do all of them with the calculator, just to ensure that you can get through these relatively quickly. What you see right here is my take on an explanation of how completing the square works, how we can go from standard form of a vertex to the vertex form, or standard form of a quadratic, I apologize, that's this line right here, to the vertex form of a quadratic. What we note from this last line is that we can compute the vertex of a parabola directly from the quadratic without having to go through completing the square, because our h value, which is the x-coordinate of the vertex, is negative b over 2a, and our k value, which is the y-coordinate of the vertex, is 4ac minus b squared over 4a. Remember, a, b, and c are your coefficients on x squared, x, and c is your constant. So the other thing that we want to identify is what we call the axis of symmetry of a quadratic. The axis of symmetry is simply the x-coordinate. It's an equation, and it's simply x equals the x-coordinate of that vertex. And you can see that, I didn't mean to cross it out. You can see that right here, x equals negative b over 2a. We look back up here, our x-coordinate of the vertex is negative b over 2a. So we are going to come up with that by example here on number 2. We have the function f of x equals negative 3x squared plus 6x plus 1. We want to find, without graphing, the vertex axis of symmetry, and then we want to determine whether or not this graph opens up or down. So first, let's focus on the vertex. To find the x-coordinate of the vertex, it's negative b over 2a. I'm going to label the values on our quadratic. A is negative 3, b is 6, c is positive 1. So let's go back and substitute this in. Negative b will end up being a negative 6 over 2 times a, which is negative 3. I get negative 6 over negative 6, which is 1. So my y, or my x-coordinate for this quadratic is positive 1. Now I can find the y-coordinate two different ways. One, I can use the formula given right here, 4ac minus b squared over 4a, or I can just take this x value of 1 and evaluate my function at 1. So when I simplify this, I get negative 3 plus 6 plus 1, which is going to be equal to 4. So I know my vertex now is 1, 4. My axis of symmetry is x equals 1. That's the x-coordinate of the vertex. And then the last part of the question says, does this graph open up or down? What I would recommend is just look at the coefficient on x squared. If it's positive, it opens up. If it's negative, it opens down. In our case, the coefficient on x squared is negative, so that means that this graph does open down. And then if we wanted to, we could actually make a pretty rough sketch of this graph without too much difficulty. We can look at graphing a quadratic using its vertex, axis, and its intercepts. So that's where the function is equal to 0. We've talked about this a little bit. We're going to talk about it a little bit more, obviously. To find the x-intercepts of a vertex, if we're looking at the quadratic formula, remember the quadratic formula is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And we can determine how many zeros that graph has by looking at the discriminant. The discriminant is simply what's underneath the radical. If that discriminant is positive, then we have two x-intercepts that are not equal to one another. If the discriminant is 0, then we have a repeated x-intercept, which means the graph essentially just touches at that point on the x-axis and then changes direction again. And if the discriminant is less than 0, it has no intercept, and it has what we call complex zeros. So that means the graph lies either entirely above the x-axis or entirely below the x-axis. So that's if you have a negative discriminant. We will look at, this is the same function that we had before, negative 3x squared plus 6x plus 1. So I'm going to go back up here and copy down. Our vertex is 1, 4. That's all we really need right now. So the vertex is 1, 4. And we have our, so let's plot that point 1, 1, 2, 3, 4. The graph opens down, so we know that this is a maximum value. What we want to find now are what are the zeros of this graph. So let's use the quadratic formula. We get x equals opposite of b, which happens to be 6, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And we will simplify this. We get 36 plus 12 over negative 6. Then we could take that a step further. It'd be negative 6 plus or minus the square root of 48 over negative 6. Trying to think. 4, 12. Got to simplify the square root of 48, which can be written as 16 times 3. So we have negative 6 plus or minus 16 times 3 over negative 6, which will give us negative 6 plus or minus 4 radical 3 over negative 6. We can reduce this a little bit as well. We have negative 6 over negative 6, which is going to be positive 1 plus or minus 2 radical 3 over 3. So that is going to be irrational, but we can still approximate that. We get, let's see, 1 plus 2 radical 3 over 3. I can type that in. One plus 2 radical 3 is 2.15, and then we also are going to do 1 minus, and it's negative 0.15. So we're going to just approximate where these points lie on our coordinate plane, 2.15 and negative 0.5. 2.15 we'll say is right here, negative 0.15. That looks good. This will be our parabola. That should not have a point like that, but you guys get the idea. So there's our parabola, opens down. The domain of all quadratics, the domain is all real numbers. So you can express it as that. You could write it as x such that x is an element of the reals. You can say x such that x lies between negative infinity and positive infinity. Or you could just write negative infinity to infinity, whichever kind of notation you want to use. You can use set notation, interval notation. Again, I did not put any requirements on how you express that. Now the range on a quadratic is also equally simple to find. If the graph opens down, which is what we have in this case, it's always going to be negative infinity to the y-coordinate of the vertex. If the graph opens up, then it will be the y-coordinate of the vertex to positive infinity. So in our case, the graph does open down, so our range will be from negative infinity to positive 4. And I did not put my inequality in there. And it will include positive 4, so we will do less than equal to. If you're using interval notation, then it would just be negative infinity 4, parentheses around the negative infinity, square bracket around the 4, and there's your range. So opens up, y-coordinate to positive infinity. If it opens down, negative infinity to y-coordinate, and that's how you determine the range of a quadratic. Example 3, graph x squared minus 6x plus 9 by determining whether the graph opens up or down and by finding its vertex, axis of symmetry, y-intercept, x-intercepts, if any, determine the domain and range, and then determine where it's increasing and decreasing. Part A is going to be relatively simple because we can actually factor this this graph or this equation, x squared minus 6x plus 9. This is a perfect square trinomial. The way we know it's a perfect square trinomial is if we take half the middle term, so half of negative 6 is negative 3, then we square it, we get positive 9, and that is our constant in this case. So this is going to factor into x minus 3 quantity squared. So does the graph open up or down? X squared is positive, so it opens up. Let's see, finding its vertex. Well, we factored this. It's in vertex form. We just didn't have that plus 0, which you don't have to write, but if that's helpful to see that, then go ahead and do it. So now we know our vertex is going to be positive 3, 0. Remember, change the sign on the h value. Axis of symmetry is x equals 3. It's just x equals the x-coordinate of the vertex. Find the y-intercept. The y-intercept can be found when you replace x with 0. So we have y equals 0 squared minus 6 times 0 plus 9. Well, we know that these two terms are going to go away because of the 0, and we're just left with 9. and that gives us the y-intercept. Had to pause the video there to plug the computer in. So we have a y-intercept now of 0, 9, and then we want to find our x-intercepts. Our x-intercepts, we look back at our factored form. We have x minus 3, quantity squared. If we set that equal to 0, we would take the square root of both sides. We get x minus 3 equals 0. Add 3. So we have a 0 of 3. So we have y-intercept, x-intercept, and the last, that's all we had to find. So let's plot all these points, and we can graph this relatively quickly now. The vertex is at 3, 0. It has a y-intercept of 0, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we also have an x-intercept of 3, 0, which is our vertex as well, so we don't have anything there. And we know also, because of the symmetry of the graph, that because we have this x, or this axis of symmetry that passes through the graph at the x coordinate of the vertex. So that means the left and right hand sides are mirror images of each other. So this point right here on the y-axis is 3 units to the left of the axis of symmetry. So we'll have another point 3 units to the right of the axis of symmetry. And this gives us our graph. If I can draw this, oh, that's terrible. That's not much better, but you get the idea. Looks like a weird absolute value. Quadratic had a baby. But that is the graph. It does open up. And the domain, we've already discussed domain, all real numbers. The range, this graph opens up. So our range is all y, such that y, or let's see, we got y coordinate of the vertex is 0, less than or equal to y, less than infinity. Or if you're into interval notation, 0 to infinity. Square bracket, 0, infinity, parentheses. Where is the function increasing and where is it decreasing? The function is increasing. Since it opens up, it increases from its vertex out to positive infinity. So it increases from 0 to infinity, and it is decreasing from its vertex out to negative infinity. And that is all you have to answer on that. I am going to stop this video here and create a second video to complete this set of notes. We're approaching 30 minutes, and I don't want to keep these videos too long. So we'll stop here and pick up in a second video.